Okay, guys, we're continuing with the next talk. Since we are already a little over time, I directly give the word to Travis Goodspeed, who is going to talk about reversing and exploiting wireless sensing. Please.
Can everyone? Testing? Hello? Okay. It's really hot up here. If someone would grab me a Club Mate, I would appreciate it. Or beer, depending upon how you want the lecture to go. So today I'm going to speak about reversing and exploiting wireless sensors locally. A wireless sensor is a very small computer which is able to survive in the field running wirelessly from battery power for very long periods of time. So while your laptop might last for a couple of hours on battery power, a wireless sensor is designed to run for months or even years. And in doing this, it can send you back. Could we turn it down just a bit for the feedback? Or could you turn the volume down just a bit? Great. So as these things are in the field, they're very cheap and you place a lot of them. In the case of the smart electric meters that are being placed out in the American electric grid, 5 million of these things have been deployed. And for security, they often rely upon hardware-accelerated cryptography that occurs within each device. Well, that might work fine when you have servers held in defended castles. But it doesn't work very well when you have wireless sensors out in the field that can easily be captured by an attacker. So in the case of the electric grid, if you steal one, beer, you're in for a treat.
First things first.
Yes. So having captured a single wireless sensor, it's worth considering how you might move that into a larger exploit. Like if you capture one node of a network, can you extract its credentials and then speak to the rest of the network, exploiting them wirelessly using network attacks and stuff that are familiar to you from, say, IT security or things like that. So I'll discuss schematic capture. Given a captured device, you want to be able to figure out which wires contain which signals. And you want to be able to do this as quickly as possible. And thanks to the hardware-accelerated I/O ports of the chips used, you can be guaranteed that the particular functions will run over particular pins of each chip. We'll also discuss the protocols that are used to send data from one chip on a board to another, and how you can wiretap that line of communication, that internal serial bus, in the same way that you might wiretap a network using a packet capture device. We'll discuss how to extract and dump firmware. So having captured this device, you want a copy of its programming. Unlike in the PC world where you can just purchase or download whatever software you wish to attack, in this space you very often have to extract it from a functioning device which has had, say, a fuse blown to protect you from, or to protect the device from you extracting its firmware. We'll also discuss simulation and the reverse engineering of firmware. So if you wind up with an application intended for a very rare chip, how do you write the tools to take that chip apart? How do you simulate the software to test for vulnerabilities virtually rather than having to crash and restart a physical unit? And we'll conclude with some observations about how to fuzz microcontrollers. So a wireless sensor itself is built up of a 16-bit microcontroller. And this contains within it all of the traditional parts of a computer. You have RAM, you have ROM, you have flash memory, sometimes you have EEPROM. And these are held within a single package, so it's very difficult to spy on what one piece of the chip says to another piece of the chip. We'll also, and then they also have a radio, such as a Chipcon 2420 or 2500, which allows it to send a wireless broadcast over a very short range. In the wireless sensor networking model, you have a mesh network of, say, 100 sensors, each of which is also doing mesh routing. And then you have sensors or actuators or something to use as input and output to make the device actually useful. And that's beyond our discussion today, because I'm telling you how to break these things, not how to run your business on them. And then they'll have serial ports for debugging. So the MSP430 is a von Neumann chip with hard fuses and a masked ROM bootloader, which means that when you capture this chip, there's an actual wire in it that breaks to secure it. And this locks you out of the JTAG port. So the other routes in are through attacking software or through attacking the bootloader. And in certain versions of the bootloader, I found a timing attack, which you might remember me presenting at the Congress in December, which allows you to guess the password 1 byte at a time. For every guess of the password you make on these vulnerable chips, the password comparison takes 2 clock cycles longer. So you can run your password, measure the amount of time, and then if you send your traffic in the correct weird way, the difference between your beginning the broadcast and getting back a non-acknowledgement telling you that your password is wrong reveals the password. This is in contrast to the AVR, which is a Harvard architecture chip. So you actually have 2 separate memories, one being flash ROM and the other being RAM. And a pointer might refer to one or the other. The only thing that specifies that is which instruction you use. And these are exploited differently. You can't write a simple Stack Overflow exploit for the AVR because you can't execute RAM. But on the MSP430, it's just as easy as in those mid-90s articles on writing Stack Overflow exploits. You just overflow the return pointer and you make the return value a piece of RAM. Further, the incoming packet is always stored at the same address, so you can be rather certain of where you should jump. Now, to figure out a schematic diagram, suppose that you've got an MSP430 1611 and a ChipCon 2420, and you want to know which pins connect them. This arrow is actually in the wrong place, but the theory holds. These 2 pins are what connect to the host PC. You know this because they are URXD0. That means the universal asynchronous serial port receiving pin 0. And then up here you see SIMO, SOMI. These are the pins for synchronous serial, which is how the radio speaks to the microcontroller. So there's actually a clock edge, and on every rising edge, the master writes 1 bit to the slave, and the slave writes 1 bit to the master. And then on every falling edge, they both sample them. So when these 2 devices are speaking, for every byte, there's an exchange. You cannot read a byte without also writing a byte, and you cannot write a byte without also reading a byte. And this becomes important when you begin reading the packet captures between them. Because when a byte goes over the wire, you need to understand exactly what that byte is saying if you're going to exploit the device or to capture something meaningful out of the traffic. And then once you've identified which pins and which rate and which protocol you want to use, you can stick hypodermic syringes into the board. These very quickly create a clean electrical signal with no soldering. Very few remaining marks will be on the device. This is a memory chip here underneath the laser. And then over to the left, this larger chip is a microcontroller. And these 2 are connected by an I2C bus, which is multi-master. And because it's multi-master, unless one of these chips is trying to hold the line open, you can connect to it as a second master, and you can just ask the memory chip for its contents while the board is still running. So in this case, I dumped the firmware that was contained within this memory chip just by tapping the 2 right pins on the top and having a regular I2C ROM programmer. You just run the commands out, and you say, I'd like a contents of memory, please, and it gives it to you. You can use the Bus Pirate to do this, or I designed a board to do it as well called the GoodFET. And in either case, you just plug it in, you send the command to read the memory chip, and for I2C it lets you. Now, to access the firmware, when it's held within an external chip, it's very easy to steal. But in the case of firmware which is held within a microcontroller, you have to use either JTAG or a bootloader. JTAG is a hardware protocol. There is no JTAG server application running within the chip. Instead, there's a hardware state machine. And the state machine allows for exchanges of bytes in a similar way to SPI. But it also has a state machine that you can wander through. So you go through different positions. There's one position that says you're shifting bytes into the instruction register, another that says that you're shifting them into the data register. And this is secured by either an EEPROM fuse, which can be attacked by ultraviolet light, or by a physical fuse, which is actually broken. And that requires probe needles. So this photo I took of Christopher Tarnowski from FlyLogic actually sticking a needle into a SIM card to tap the internal memory bus. And you can actually see the needle right here on the left. And this requires a lot of skill and a lot of equipment. But it's not necessary because you can use attacks on JTAG and attacks on the bootloader. You can do voltage glitching, which is where you just drop the voltage and bring it right back up. And if you do this very quickly, the chip cannot distinguish between this as an intentional attack and this as an accidental problem with the supply voltage. And if you do this at the moment that the flip-flops are latching in a value from a previous stage of the microprocessor, such as if you're fetching a value from memory, and the flash memory circuit is presenting that value in response to being given the address, and the value is about to be latched in to be, say, written to a register. If you glitch at that exact moment, the logic signals at that point will mess up, and the wrong ones will be latched in. This allows you to misexecute an instruction or to skip an instruction. So in the case of the MSP430, if you have a -1 or FFFF as an instruction, it does nothing. And you can force in NOPs like this by controlling whether the voltage is rising or falling at the instant that a loaded instruction is latched. You can also do a timing attack where you look for a piece of code that behaves differently, say for a correct password as for an incorrect password. And having found this, you run it both ways. And you have complete control over the chip when you're trying this. You can watch every bit of the output. You can watch the timing of that bit. You can vary your own timing to try to get the receiving chip to misbehave. So if they scrub timing after you present a password, you can actually gamble your serial traffic upon where the timing should be as it's listening. And then even if there's a delay between receiving a password guess and actually sending the reply back, you can still measure the timing of that guess. This is a BSL cracker, which I built to exploit a timing vulnerability in the MSP430. And you can plug this up to a vulnerable wireless sensor, and it connects through the upgrade serial port. Then it runs, and it presents invalid passwords, just sort of iterating them until it figures out what each byte is. And they fixed the problem that this exploits and then reintroduced it again a model number later. This is a scope photograph of a voltage glitch. From here to here is half of a microsecond. And you can see the glitch occurs and ends within 50 nanoseconds. This is a recording of the power consumption of a chip. Once you capture a wireless sensor, you can knock the decoupling capacitor off of it. And I'm sure you've seen the side-channel power analysis attacks against smart cards. But this works differently in that you're not really trying to figure out what it's computing, so long as when it's computing it. Because if you want to glitch, you want to do it on one of these falling edges, which are the moments at which a clock edge occurs. Because on a clock edge, a CMOS transistor will flip. And it's only when a transistor is flipping in CMOS that it consumes power. In the case of the timing attack that I keep coming back to, if you have code like this, like if A does not equal B, then clear the allowed bit of the access variable. This format here where you do like and equals and the tilde to invert is very common in embedded C programming. But if you have this code, it takes longer to run if A does not equal B because it has to run that clause in the middle. And you can measure this. So on the left, you see the number of clock cycles that each simulation took to run. And you can see that some bytes, 0, 0, 11, 3A, they completed faster. The difference of clock cycles divided by 2 gives you the number of times that those bytes occur within the password. If you see this password on the right, you'll notice that 3A occurs 15 times, just as predicted. 11 occurs 16 times, and 0 occurs only once. You'll also note that this password isn't very random. It wouldn't take you terribly long to guess this if you knew the general pattern. And the pattern is that every one of these words is an address in memory at which executable code exists. This is the interrupt table. So when the machine turns on, it looks here at this word, and that's where it begins execution. All of the unused variables have the same word in them. So if you were trying to brute force this, you could do it in very few attempts by assuming that the startup word, this 1100 here, always points to the beginning of flash memory, which on this chip is 1100. And then you just start counting up the other word until it latches in, and that will break any application that doesn't, say, rely upon interrupts for power efficiency or for button inputs or for things like that. If you have one that does use those, then you can guess which words will be outside of this pattern. And there are different strategies for guessing it. In a full application, guessing it becomes infeasible without the timing attack. But if you have an amateur programmer, or if the only purpose of writing the program is to test the timing of the password routine, then it becomes a lot easier. And you have further complications. You have a start bit. So in asynchronous serial, when you have an incoming byte, the line stays high and idle until that byte begins to be transferred. Then the line drops low for a single bit. That's called the start bit. And then the rest of the bits are sent least significant first. But if you look at the code inside the chip that's actually implementing this serial port, it will have a while loop that spins until the line drops low. And if you know about this loop, then you know that doing a timing attack, you'll have to drop the line low early and then gamble it when the entrance of that loop would occur and begin shifting your bits out at that moment. I was lucky in attacking this in that you can slow down the serial traffic. You can make it speak as slowly as you please. You can even slow down the clock on some versions, which is handy. And then when you disassemble the code, you're dealing with a very different environment from a PC. On a PC, you have 4 gigabytes of address space, and that's in 32-bit mode. You have a kernel to deal with, and you have other processes that are playing along. If you're trying to hide code on a PC, there are all sorts of nooks and crannies that you can do it in. You can use the memory manager to actually change the view of RAM to a particular process. You have a hypervisor, and you can infect the hypervisor, and you can all of that crazy stuff. But none of that works on an embedded system. And none of this works on an MSP430 or an AVR, because you've got a small address space and a single process. You have no kernel. You don't even have a runtime linker. You have no dynamic symbols of any kind. In many applications, you won't even find function pointers. But at the same time, there's no I2Pro support. You have to write your own tools to do these things when you're the first person analyzing code on a given chip. So I wrote a quick tool called MSP430 Static that I really wish someone would replace. It's written in Perl calling SQLite, which calls back to Perl, which would be suicide if you were trying to do it for a PC program. But the longest word that physics will allow on this, the longest program that physics will allow in this chip is 32,000 words. A 32,000 row table is not that difficult to query. So you can write a query. You can select the hexadecimal address of a function along with its name, ordering it by the addresses in descending order, and you can limit that to 5 results. This will give you the 5 functions that are in the highest regions of memory. And this is useful if you have an application that's mixed in with a bootloader, because the bootloader will be above a given address. You can draw memory maps very easily just by selecting code out and piping the rows through something that translates it into drawing instructions for a graphics program. Here you can see a very small program that begins around 4,000 hex. The application data is in red. The executable code is in red. And it's easy to recognize executable code because it disassembles cleanly. Even though there are 16-bit instructions, not all values for a given instruction mean something. So wherever a given instruction is valid, you draw that in red, and wherever it's invalid, you draw it in gray. You'll wind up with solid red for executable code and mixed red and gray for unexecutable code. And this allows you to distinguish between the two. You can also count upon the compiler placing them in particular regions. So in the case of GCC, executable code comes first in flash memory, followed by data. You'll also note that with many compilers, the data will immediately be copied to RAM as a bug. So if you find the same content in both RAM and ROM, you can be reasonably certain that it's data and not code. This is a more complicated image, one taken out of a physical device. This is a JTAG debugger that Texas Instruments sells for debugging their chips. You can see here in red is the main application code. Up here you have data tables, which are loaded in for identifying target chips. And then at the very top, this red code here is actually a bootloader that proxies interrupts to lower code. And because it proxies interrupts, the password will be the same on all versions. And you can actually separate these two applications. To separate individual functions, you can bank upon there being only a call to an immediate value. So wherever you see a call or a branch, you know that the address that comes after it, which is often a distinct word and very easy to search for even in binary code, you can bank that that word refers to the entry point of another function. And you can find its exit point because the exit point will be after the last relative jump. So if I have a JZ or a JNZ or another jumping instruction, after a comparison, in say an if statement or a while loop, or if I have a switch, there will always be a default clause which jumps to the end of that. So look at all of these different relative jumps, and the return function will always be after that. Once you know where functions begin and end, you can figure out which ones call each other. So you can search through a function, you can say, give me all of the targets of call instructions. And then you can generate a call graph from this, where every function is a vertex, and then every function call is an edge in graph theory. And there are great tools in Unix for rendering these. So here you can see a reasonably large application. All of the unused interrupts come as this sort of long jump here. And you can find particular functions very easily because I/O is mapped to a particular address. Your output buffer for the first serial port will always be at the same address. So if U0's transmit buffer is at 77 hex, and you see an instruction that says move the byte in R11 to 77 hex, you know that that instruction is writing an output byte. If you know what's plugged into that port, which you can easily find by looking at the board and tracing the wires, then you can tell that this, say, transmits a byte to the PC, or this transmits a byte to the radio. And then you can give it a name. And you can search for the list of your names very easily through SQL or whatever you might write your own tool in. Then you can dump out a hash of that, and you can compare future programs to it. If you have access to example libraries, you can build up databases of the hashes for all of the standard functions, and then you can identify them later. And the MD5 checksum of the code is not a creative work. It's not copyrightable in the same way that the code might be. So even though I can't give you a copy of the code that I've identified, I can give you a copy of a one-way hash of that code along with a name that I've given it. And I can include this list with my tool. So when you're running the tool, you type 2 commands, and it will recover the name of every function in your application that I've seen in any of the functions that I've ever taken apart. You can also look by call frequency. There's an operating system for this called TinyOS. And it does a lot of mutual exclusion calls. So if you look at a graph, it'll be this rat's nest where 2 functions get called 1,000,000 times. And those 2 functions are atomic start and atomic end, always. If you have a new large application that's complicated, not something small, and you search for it for the most popular functions, it'll probably be these 2 if it uses multi-threading. You can also look at the interrupt table, because in the same way that there is a standard word at which you write all of your outcoming bytes, there's a standard address at which the operating system looks, not the operating system, at which the hardware looks to figure out where to jump when an incoming byte arrives. And you can run through this list, and everything has a meaning by hardware, so you know that it will apply to your firmware image. The timers, for example, will usually jump to task handlers, and the I/O will usually jump to button handlers or things of that nature. It's very expensive to poll a switch to see when the button has been pushed, as far as power is concerned. So you don't do that. Instead, you put the chip to sleep, and you say, wake up and run this interrupt handler when the button gets pushed. But you can't specify which. That's done by hardware. And that makes it easy to reverse engineer. And then you can see here that these interrupt handlers are all unused. So if you see many different interrupts going to the same target, it's probably an unused handler. All it's doing is making sure that the chip doesn't crash by some invalid address being pushed in by mistake. You also have to worry about function inlining, because on these platforms, having such little RAM and such little stack space, it's more efficient to inline a function and save that call on the stack, even if you have enough flash memory to hold it. Because the code executes from flash memory, it does not execute from RAM. And in simulating these, you might want to dump out things to show you how your application is running, or whether it's working. Or if you're trying to take something apart, you'll want to poke its different I/O addresses, or fuzz it virtually, rather than in hardware. So I'll be showing you an example of a Stack Overflow in simulation. This is on a von Neumann chip in which RAM is executable. So it's the easier type to overflow. To exploit a Harvard chip, you have to actually call existing code, or rather the tails of existing code, to move your attack from RAM into flash memory. It becomes rather involved. So here I did a nice little simulation to beamer dump, and I can single step through it. So as main begins, it's going to call load, which has no exploit, no exploit occurs here, and then load over, which it does. And each of those will call string copy. So as I advance, you see the program counter goes to 1170, which is the load function. Then the load function grows the stack as it enters. It then calls string copy. String copy begins writing, and you'll see Cafe Babe be written to the stack. And it stops copying when it has a null. This is just a standard Stack Overflow exploit that ends on a null. And then that function returns, and for load to return, it's going to pop the stored value in main, that's 11E0, into the program counter. And it does this, and then main calls load over, and you can see load over begin writing everything with Fs until it's told to stop. And then it will overwrite the return pointer with 210. Now the return pointer has been overwritten, and as the stack rewinds, it's going to jump into RAM instead of the place that it came from in main. And this is how you perform foreign code execution on a microcontroller. And with wireless sensor networks, you can do this because they're on a network. And you can speak on that network as soon as you compromise one of them. And you can fuzz these things. You can do it either being omniscient or blind. So in some cases, you might want to rip the code out of a microcontroller without knowing what's already there. To do this, you start injecting fragments that might reset the chip. And you keep doing it until you can make it return into the bootloader. You know it's in the bootloader because it's masked ROM. It's the same on every chip. So when I was attacking one of these with Aurélien Francione, we started sending random packets. And the random packets would have just repeated fields of the entry point of the bootloader. And then we just waited for the bootloader to start up and say hello. We could tell this because a certain I/O pin would become an input pin. Whenever we failed, it would just reset and we could get another try. And on the few cases where it locked up, we just hit the reset button. And this worked very quickly. And then once we had that foothold, where we were in the bootloader, but we didn't have administrative access to the bootloader, then we could change our exploit code. Then we could make it elevate our privileges before it returned. And we found a blind way to actually use the code that was already in flash memory to pop a value into register 11, which controlled the access privileges. So we set up our exploit to run existing code within flash, not knowing where it was. And since we already knew the field offset, we could just guess at the address that we would return to. And sure enough, 20% of the time, it falls exactly where we want before it locks up. So we can hit the reset button a couple of times, and in 3 or 4 seconds, we have access to the device. You can detect a reset of the chip because all of the I/O pins become high impedance inputs. If you have an output pin and you put 2 large resistors across it, one going to VCC and one going to ground, the output will ignore those 2 voltages. But if you have an input pin, then the value will be the fraction of those 2 by the difference in the voltage. So if you've got a 100 ohm and a 300 ohm, then the voltage might be 1/4 of the high voltage. And this is easy to measure, this is easy to detect, so you can tell when you've caused the chip to crash and reset. So you can fuzz it to create a crash, and then having found the crash, you can adjust your offset until you get execution of code that you know to already be within the device. And then you begin trying to execute foreign code. So in the case of von Neumann chips, you can just return straight to RAM. In the case of Harvard chips, Aurélien wrote a neat little paper on using return-oriented programming for microcontrollers, in which he was actually able to use enough of the existing code in a wireless sensor to move an exploit from RAM into flash memory so that it could be executed. And he did all of this movement without being able to run any of his attack code. It was at CCS in 2008. It's well worth looking up. And then together we just published a paper at the Usenix workshop on offensive technologies that describes how to do the blind return-oriented programming, calling code in flash memory, just guessing that it will be there by the ways in which compilers arrange things. So in our case, the compiler would open every function with push R11, push R10, push R9, push R8 to save the values in those registers before changing them. And then it would end with the opposite sequence. Pop R7, pop R8, pop R9, pop R10, pop R11, return. And the credentials to the master ROM bootloader were stored in register 11, which means that the fragment of code we wanted, pop R11 return, was actually the most common sequence of 4 bytes in all of flash memory. So it was very easy to find that location by guessing. I've been doing some work on a neighborly Tennessee belt buckle. You might have seen a Shmoocon, which actually is a wireless sensor, and it runs around by broadcasting random strings. And then when it receives a string, it puts it into a small buffer, and then it replays it, along with a random reply. So if you have 2 of these together, they just start bouncing back and forth, and they display the packet on their LEDs, and they blink, and you can say, hey, I've got a belt buckle too, and everything is grand. If you're in the field in the middle of nowhere, it'll just sit there silently and occasionally broadcast a short thing to look for another belt buckle. But if you have one of these in the presence of a regular Zigbee network, it starts broadcasting random packets with valid checksums that are part of the MAC protocol, just in response to anything that it hears. So it starts fuzzing everything around it. I won't actually be releasing this, but I've only had one person come up and tell me while I was planning to release this, you know you will kill someone, right? Because medical equipment runs on this. You have like pulse oximeters that you can clip onto the finger with no external power supply that will send patient data to a computer without having a tangled nest of wires. You have fly-by-wireless in aircraft. The electric grid is running on this technology now to signal changes between electric meters. So I've covered all of these things, and I've had to skip over a few exploits that I might have otherwise presented in more detail. And I've got plenty of hardware to play with. So after this lecture, I'll be going to the hardware hacking village in the BSD tent. And if you'd like, we can play with my equipment, and I can actually walk you through some of the exploits of wireless sensors. Or we can stick an oscilloscope into one to spy on the traffic that's occurring within it. I've also got packet sniffers for ITC and SPI, so you can watch commands run from the microcontroller of the board to the radio, and similar things. But have you any questions? Or come on, somebody, be neighborly.
Well, if there are no questions this time, I will be taking the opportunity to ask the first. You shortly addressed the AVRs. The difference between von Neumann and Harvard. Can you elaborate a little bit more how you how you exploit these AVR because of these different architectures?
So you can exploit AVRs by attacks against the voltage and their debugging framework. Traditionally, voltage glitching has only been used to attack software within a chip. As you're running an application and the software is fetching a byte from memory, you can glitch at that moment to make it fetch the wrong word. You can use this to bypass the access controls. But you can also do the same thing in hardware, because where there is a hardware debugging mechanism, it is also a digital machine that operates on a clock. Even better than this, you control the clock externally. So in the case of the AVR or the MSP430 or any other chip with hardware debugging, you can connect with the debugger and send it the command to give you access. It then looks at its memory and sees that you're not allowed to have access. So the state machine runs from 3 states. It begins in like a wake-up state where it fetches this value from memory. Then it proceeds into a fuse check state where it looks at this value and decides whether or not you're allowed entry. And then it goes to a 3rd state, which locks you out. So you have 2 state transitions. You have one from the initial to the check, and another from the check to the deny state. On each one of these, if you can mess with the value that gets latched in, you can fall into a random state. And in the case of JTAG, you've got a map that they actually give you as part of the standard. And if you look at this map and you pick any random location, you might land in the state where you are loading a word into the instruction register. You can always navigate from there back to the beginning by sending the right sequence of bits on the right input pins. So all you do is jump ahead of the fuse check and then navigate your way backward to the beginning where your debugger will work. Yeah. Yes? All right. Well, thank you and have a nice day.